Welcome to the 25th lecture in mechanics of materials. Till now we have been looking at problems wherein the loading was confined to one of the axis and the axis was what is called as a principal axis, so that the bending or the displacement takes place along in a particular plane, or the displacement, predominant displacement is along the y axis. Okay. So, now we saw that when we introduce bending moments, there can be bending either in the z direction or y direction, depending upon which the deflection would be in y direction or the z direction, right. Okay. So, now we will go about and see what happens when the loading is on both the axis or the loading is not about the principal axis. Okay. So, till now what we have been looking at is this case, this case when you have a beam with some support conditions, hinge, roller or a fixed end subjected to some loading along one direction. Okay. Now what we will do is, we will, apart from there being loading on the y direction, there can be load coming on the z direction also, that is there can be loads acting like this in this beam. Okay. There can be loads acting like that on that beam. Then we will see what happens, how do you analyze such a scenario, and also in all these cases that we consider till now, the cross moment of inertia or IYZ defined as integral yz dA was 0. Okay. It need not be always true for some oriented axis. Okay. So, let us first understand how to compute moment of inertia about an arbitrary axis, not necessarily the principal axis, and then we will see that there will exist always an axis in about which IYZ will be 0. Okay. So, we will determine that axis and then we will see how to analyze the beams subjected to bending moment through that axis, loading through that axis. Okay. So, first what we are going to do now is, we are going to look at moment of inertia about an arbitrary axis. Okay. So, let me assume that the cross section is in the shape of a potato and I have some axis y and z taken like this. For this I can compute IZZ, that is the moment of inertia about the z axis, which is y square dA, area of the cross section, and compute IYY, which is integral z square dA, where integrated over the area of the cross section, and I can define IYZ, which is integral yz dA, integrated over the area of the cross section. Okay. Now, say as usual, like what we did for the stress component, strain component, this moment of inertia about an axis or in a particular direction, but two of us need not agree on this orientation of the axis. So, let us ask the question, what happens if someone comes and rotates this axis the anticlockwise sense to y star and z star, where this angle is theta. Okay. Now, what happens, z star would be integral y star square dA, same area of cross section, and y star would be integral z star square dA, again over the area of the cross section, and y star z star is going to be integral y star z star dA, area of the cross section. Okay. Now, what is the mapping that will take from y to y star or y star to y and z? Y star can be written as y cos theta plus z sin theta, just like taking the component of forces, y star is y cos theta plus z sin theta, and z star would be minus y sin theta plus z cos theta. Okay. Now, I substitute for y star and z star into the expressions here. So, what I do is I substitute this expression for y star in here, this expression for z star in here, and y star and z star in there, and I expand these equations. Okay. Then what do I get? I have to find y star squared, that will be y square cos square theta plus z square sin square theta plus yz sin 2 theta, that is 2 yz cos theta sin theta is yz sin 2 theta. Okay. And similarly I get z star squared as y square sin square theta plus z square cos square theta minus yz sin 2 theta, and y star z star would be y square minus y square plus z square cos theta sin theta plus yz cos square theta minus sin square theta, okay, minus y square sin square theta, cos square theta minus sin square theta. Now, so what does the expression I z star become? This will become integral y square dA a cos square theta plus z square dA sin square theta plus integral yz dA sin 2 theta. This is nothing but I z cos square theta plus I y sin square theta plus I yz sin 2 theta, right. This is I z star. Okay. Similarly, you can see that I y star which is z square dA, which is this z square dA is square of this, which is this. So, if I substitute in there, what I will get is I will get I z sin square theta plus I y cos square theta minus I yz sin 2 theta. Okay. Similarly, I y star z star is I y minus I z by 2 sin 2 theta plus I yz cos 2 theta. Okay. Where I use the fact that I use the following equations. I use the fact that cos square theta minus sin square theta is cos 2 theta, and I use the fact that cos theta sin theta is sin 2 theta by 2, and minus y square dA would be I z minus I z and z square dA would be I y. Okay. That is what I have used to find this expression in here. Okay. Now, what we have to understand next is we have to answer the question, how does this transformation look like? This looks like similar to the Mohr circle equations, right. Okay. So, this equation I can rewrite it as I z plus I y by 2 plus I z minus I y by 2 cos 2 theta plus I yz sin 2 theta. This is exactly the Mohr circle equation, right, and this is also the same form. So, I z star y star plays the role of the normal strain or the normal stress, whereas I y star z star plays the role of the shear stress or the shear strain, right. Okay. So, this transforms just like the Mohr circle equations. Now, what is the property of I normal, what is the property of I z star or I y star? They are going to be always positive. This will be always positive, right. because it is a integration of a positive function, y square is a positive function, so they will always be positive. So, in the Mohr circle equations, if you look at, if I plot I x I y y or I z z along the x axis and I y z along the y axis, then my circle would be something like this. Okay, my circle will be something like that, wherein there will be positive I y z and negative I y z possible for certain orientation of the axis. Now, let us understand why that happens physically. Okay, why there is a positive I y z for some orientation of the axis and negative I y z for the some other orientation of the axis. Okay. Now, let us say I have this cross section, some potato with y and z initially oriented like this. Now, say I change the cross section to some orientation y star pointing like that and z star pointing like this, that is I rotated the coordinate system by 90 degrees. Okay. If I rotate the coordinate system by 90 degrees, what happens? What is I y star z star? Substitute 90 in there, it will be cos, it will be I y y minus I z z by 2 into sine of a theta rotation, the coordinate system is 2 theta in the Mohr circle. So, theta is pi by 2. So, 2 into pi by 2 plus I y z into cos 2 into pi by 2, this is minus I y z. So, because sin pi is 0, cos pi is minus 1, so this is minus I y z. So, if I y z is positive, I y star z star will be negative. If I y z is negative, I y star z star will be positive. Okay. So, there is a flip in sign by for a 90 degree rotation of the coordinate system. There is a flip in sign for a 90 degree rotation of the coordinate system. Okay. So, what this means is, before that there will be a point where I y z will go to 0, that is between 0 to 90 degrees there will exist the orientation of the axis where I y z is 0. Okay, because I y z is a continuous function of theta and it changes sign as the theta varies from 0 to 90 degrees, and hence there will be a orientation of the axis for which I y z will be 0. Okay. That I y z axis where it is 0 is the principal axis. Okay. So, there will be corresponding to the principal axis there will be a point which has, say the principal axis is denoted by u and v, there will be a point where it has a minimum moment of inertia I v v and a maximum moment of inertia is I u u. Okay. So, we are interested in finding this I u u and I v v and the orientation of u and v with respect to x and y and z. Okay. So, that is the principal moment of inertia, the orientation of the axis of the principal moment of inertia. Okay. Okay. Now, what is that? The question is, what is the orientation for which I y z will be 0 or I y star z star is 0 implies tan 2 theta is 2 times I y z divided by I z z minus I y y. Okay. So, the orientation of the u v axis with respect to the y and z axis is given by this, theta is principal axis is 1 half tan inverse 2 times I y z divided by I z z minus I y y. This is similar to finding the principal stresses or principal strains and the orientation of those principal stresses and principal strains. Again, you have to be careful when you do this tan inverse operation. The angle has to vary now between 0 and 360 degrees. So, it matters whether numerator is positive, denominator is positive, numerator is negative or denominator is negative or both are negative. All these 4 things will determine which quadrant the axis is, what is the theta for that corresponding. Okay. So, you have to be careful there. Okay.